Hello, everyone. Welcome to Practical GCP. So about a month ago, I created a video on showcasing how to deploy the DeepSeek R1 7 billion open source model to Cloud Run. And I've got some really good feedback on that one. And also at the time, I only knew about one way to deploy it, which was Ollama. So I tried to see kind of if it works well, what the concurrency looks like. Uh, but based on the feedback, and thanks everyone for commenting on the video, sending me alternative options on LinkedIn as well. So basically, I've since learned about the VLLM, which is another way you can deploy open source models to such as Cloud Run in the containers, and also HuggingFace TGI, which is another interesting option. So in this video, I want to do a more of a deep dive on how I actually tried all three and compared all three in trying to optimize, again, the same topic on how to deploy the models concurrently. And what the performance looks like, what the different ways I try to optimize the deployment process. So I think it should be very interesting. So I would like to share that with you. So let's crack on. So first of all, I want to go back a little bit on why I actually even care about this stuff, right? Why open source LLM matters. So there's obviously many angles you can look at this. One of the key three things in my head is one already talked about in the last video. Is about security, right? So if you are in a large organization and you need to deploy LLM models, for many organizations, literally sending data to a different organization that just via APIs is not an option, right? So that's one of the things. And also the ability to use a smaller model such as the R17B is actually you can fine tune the model to be very, very specific to what you need, whether that's some specialized knowledge that you have in your building your SaaS products or something that you want to do internal or keep it internal to your organization, and you can fine tune the models to actually achieve that, and it's much cheaper to do that on a smaller model. And you can't really do it if it's not open source either, right? So, and then the cost control side is, especially when running with Cloud Run, you could easily set up the minimum maximum containers you want to scale up to. And that's important because then how much it's going to cost you. You can tune it, and if you use the models just via API calls, if they increase the cost, then you're already in a not very good position, right? So this just gives you more options. But obviously, there's other areas you can do local testing. You can provide better SLAs because you now don't need to rely on a third-party service to do this. And obviously, you have more choices because the advancements of open source model is very rapid, right? So in terms of Cloud Run, a few of you asked me can you talk a little bit more about Cloud Run? Why do you not deploying anywhere else? So I'm just going to talk a little bit about this. In terms of Cloud Run, first of all, is you would have something very similar on AWS and Azure. Is basically a way that you can use a serverless infrastructure to deploy container-based workload, right? So it's serverless and it's container-based. There's a few key benefits and why Cloud Run is one of the flagship products in the Google Cloud ecosystem is because it has immediate scale. So that's one of the things that's quite different to Kubernetes. And usually for Kubernetes, I created a video a long time ago that where you have to use something called the balloon pod to be able to scale things fast in seconds, but then you still have to pay for it, right? So with Cloud Run, you have this in second immediate scale from 0 to 1,000, right? So that's something that you can do with literally zero setup. And this is not something you typically get in a Kubernetes cluster. And also the ability to scale to zero. So this is really important, especially now you have the GPU support in Cloud Run. It's currently in preview on the GPU support, but scaling to zero is a big deal, right? Why is that a big deal? Because your traffic is not always on, right? Scale to zero, not in addition to auto scaling, but you can also scale to zero. What this means is the minimum GPU you can use at a particular time could be zero, right? And that is important. And it goes down very quickly when you do not have any traffic. So this is very important for internal use for organizations where you don't have anyone using those APIs, or for when you have quiet times, and then it basically scales up and down, but it can't go all the way to zero. So this is important. So in terms of the three I've done and compared with, so that's Ollama, VLLM, and TGI. So keep in mind that I'm not expert on either of these, right? So what I'm trying to do is to see, because I think not just myself, but quite a lot of you are quite new to this, and I want to focus on the least amount of effort, but I try to optimize the deployment process based on the default setup. So what that means is I don't want to just spend so much time tuning this. I just want to see what the default looks like, and I'll probably tune a few things and to obviously optimize for the deployment and concurrency to see what it compares, what it looks like between the three options. So I want to give a quick, like a one sentence kind of understanding from my perspective what the difference between the threes, right? So Ollama, it basically simplifies running and fine tuning LLM models. You can actually do it locally, but especially for developers like who want to be like have it very easy to use. This is really good for local testing. It also has an API, a REST API, which is why in the original video I thought maybe this is something I can use for production use case, and it did work. But for the other two options with VLLM, this is much more optimized option for high performance inference, and it's optimized for speed. And one of the issues I had in Ollama was it wasn't very good at utilizing the memory. But VLLM by default actually try to utilize and optimize the memory consumption, especially GPU memory. With TGI, HuggingFace TGI, this is actually a very interesting option. And one thing actually Google has well documented on their documentation on using this as one of the options as well. And it's also they claim a robust production ready inference server for deploying LLM scale, right? What I thought is if I try all three based on the same model, look at the concurrency, looking at the deployment time, how quickly the things can scale up and down, and a few other parameters. So this is what kind of drove me to create this video, and because I did all of these things and I want to share that with you, right? So in terms of the DeepSeek model, right? So I want to spend a little bit of time talking about the R17B and specifically the definition of a distilled model. This is a term I didn't understand that well, have to be honest, even just like 1 or 2 months ago. And it seems to have caused a lot of confusions to myself and then to many colleagues and people I know as well. They don't seem to understand the difference. Some say the distilled model is just garbage, it's useless, but some others say this is really good, comparable to O1, what is going on, right? So I did quite a bit of research and reading, and also look at the not just the benchmark, but actually look at the answers it gives in specific categories. So keep in mind specific categories. So my understanding is this. So the original models, such as the DeepSeek R1 600 billion model, those are trained from raw data, which means you need a lot of GPU, like a compute, to be able to do that, and it takes a very long period of time. It costs you a lot of money, and those models usually score very high across all categories, because they're very comprehensive, right? But where you get to the student, or this is where the distilled model is coming from, they are trained based on understanding of those teacher models, such as they're distilled from the R1 600B on what's most important in certain specific categories. So R17B in this case is very good at, you can see in here in the comparison, is on par with O1 Mini, right? O1 Mini is a very capable model, but it's nowhere near in some other categories such as coding, right? You can see it's only like a 37.6 versus 53.8. But in other area where it comes to math, it is actually outperforming O1 Mini. So this is important detail to understand because it's not good at everything, but it's good at in certain things. But there's a few key benefits in this. So one about this is smaller in size. That is important because R17B is only about 5 gigabytes. If the model is too big, you can't really fit it into smaller GPUs, such as the NVIDIA L4 that I'm using in this case in Cloud Run. And it also has faster inference time, right? Because it's smaller, it's more kind of lightweight. in terms of fine tuning, this is very important because if you have an open source model and it's small, you can fine tune it with your own specific domain knowledge, and this doesn't actually take you a lot of time. One thing I thought from one thing I saw from the statistics, what one is claiming that you can even use a consumer GPU to fine tune a model of this size in under 4 hours. So that I haven't tried this myself, but it's actually very significant if that's true. And obviously scalability, right? If it's small, it can hopefully serve more concurrency, and then it can be cheaper per user or per request, right? So let's spend a bit of time talking about this. I hope this is actually clear, and it's important, I think, to understand the difference, right? Okay, now let's look at some details. I'll start with Ollama because this is the one I did a couple of weeks ago. And in terms of the setup, I've used, again, the same model, which is the R17-bit Distilled. I've bumped the CPU core and the RAM into 8 and 32. This is because I tried to kind of use the same setting across all three. And with half of the resources, that's the minimum, which is what I used with Ollama. It doesn't actually work with some of the others. So I want to keep it the same to see what it's like. But in fact, the CPU cost and RAM doesn't actually affect the inference performance from what I can see. But it is something will affect how quickly things can get started, right? So in terms of the GPU, there's currently only one option in preview is the L4. The L4 is actually quite powerful. It's got 24 gigabytes of GPU RAM, so it's not like tiny. This can fit in actually more powerful model than the 7B. But I couldn't run the 32B, so it seems like you have to run something in between. So with Ollama, what I did was I've used I've cached the whole model in the container image and pushed into artifact registry. So this is the important detail because you see what I mean by that later on. So when I actually use this, you can see the code start time. So this is when you scale up from 0 to 1 to 5 or anything like that. It only takes 4 to 6 seconds to scale up, right? This is the major difference compared to some of the other options we'll show you in a bit. But you can see I flagged certain things in red, which is concurrency. And I was only able to achieve 5 per container in Cloud Run. That's with the Ollama's deployment. So this is the stats I've got from the last time, right? So now with VLLM, this is very different. So all of the parameters I kept the same. There's one thing I made it different, which is the GCS Fuse mounted to Cloud Run as a volume. The reason I wanted to try this is because there's others like gave me feedback on what if you use GCS Fuse, and that's gives you more options to deploy models in a way that is much easier to swap the models, because the way apparently if you do it in the container, you have to build many different containers, right, to use different models. So this gives you a lot more option. But I want to understand what is the cost on the cold start time, right? So it actually surprised me quite a bit. So you can see, let's look at the red ones first. Start from the cold start. The cold start is actually 3.5 minutes. That is really slow, right? So the setup with the GCS Fuse is already based on a VPC connector using the PSC setup. So this is already the most optimized way to do this. And if you don't use the VPC connector, and it doesn't even work, right? It takes forever and it hangs and it dies. So I've tried it without. So you have to use the VPC connector to even make this work. But the time to start is still very slow. I'll show you some of these in the demo later on. I'm gonna in more detail. But that's what I found, right? So it's not actually that impressive on using this approach. The other thing around this is the max token size. So I realized with the VLM default setup, I've tried to change a few things on the maximum return token on one of the other ones. I can't remember the details, but it can't pass beyond maximum token size. So this is the one that returns from in the output beyond 512 tokens, right? So this is quite low compared to Ollama, which can do the above 2000s, which is now much more usable. But the concurrency shoots up to all the way to 30 to 60. And that's a major difference. And this is really, really important. Let's say even you can run the 512 maximum tokens, and the actual concurrency with the relatively minimum latency, you can still go to 3 to 60 concurrency. That is massive, right? Just think about it. It's just one GPU like this, and it can serve this many 3 to 60 users concurrently using your solution, right? Although it has some drawbacks in the other categories. Right. Now let's look at TGI, right? TGI, well, it's not very hard to see that you can already see I'm leaning towards to this option based on the stats. And this time the difference here is because I've tried the other two options to deploy the model. Now this time I've tried to use the download option, right? So I was quite skeptical about if I download it, would it take longer? But in fact, it only took 60 seconds to get that model to your container and then ready to serve for traffic. It's not just download; it's ready to serve traffic as well. So obviously, with this option, you're going to need internet access, right? Which is not an option for all organizations, but it's there. And because you don't really do much with the models, the internet access is isolated for this particular service. The risk is pretty low, but it only takes 6 seconds, which is quite surprising to me. But let's look at the maximum token size and concurrency. So the concurrency is very, very similar to VLLM. However, the max token size can go all the way to 1,000 or even beyond 2,000 return tokens. This is a big difference in that, and it can still retain a token per second. For each one of those requests between 12 and 15, and that is a very good thing, right? So before I go to compare the all three, I want to show you a few things that I've seen in the stats. So if you look at this, the request latencies for a lot of this, even when it has very high concurrent request, you're only talking about like a 0.66 minutes on request latencies, which is very good. And obviously it will go up this is talking about TGI, right? Obviously it will go up if you increase the max token, because it just takes longer to generate those, right? But generally, if you have a smaller max tokens, it actually can achieve very good latency. What's more important is this diagram. So you can see that I can achieve 64.9 per instance concurrent request with the startup latency when it scales up to only like 1.2, 1.3 minutes. That's like 70 seconds. This is actually very, very good. And then the most interesting things around the GPU memory usage and utilization. You can see this GPU has 24 gig, right? That's the total, but it uses 20 gig in terms of utilization. That's like really, really good. And then the memory utilization is almost close to 100% at all times. So this is what you want to see, because the other ones, when I was especially running in Ollama, it was very low down here. It wasn't actually using much. So this means, I think that's the major impact on why the concurrency was very low. You can probably tune it, but this is not something I have to do at all with TGI, right? It's just automatic. And the GPU utilization still goes up to 100%, which is expected. So now let's look at all three together between Ollama, VLLM, and TGI, right? So you can see from I've compared it in the number of categories. I've also put a bit more things in there so you can compare the cost per request, which is very useful to know. But from the Ollama's point of view, because it has a relatively low concurrency, and it's not actually good for production use. So you can still use it for local testing. It has REST API. You can deploy this way. It is easy though, but it's not efficient enough. It can be quite expensive if you have a high amount of concurrent users. With the VLLM, it has really good concurrency. It has really good code tokens per seconds per request based on the P99. I tested in there. However, the token size on the max token size on the the amount of tokens you can generate in the results is very low compared to the other two. So I cannot make it pass beyond 512. It just basically gives me the 504 error code and times out, and it's very hard to figure out. I spent quite a few hours tuning and changing different parameters. I cannot make it pass beyond that, and that's a issue I've seen in there. So this although it has a high error rate beyond 512, but for 512, below 512, it has very, very good concurrency and very, very good token per second with the P99, right? So TGI, obviously, you can see there's quite a lot of green here, and that's just because it is actually that good. So you have the 30 to 60 concurrency, same as VLLM, but on the max token side, you can go beyond 2000. And this is a major improvement in there. And you can still achieve a token per second. I think when it gets to about 2000, you get about 12 or maybe a little bit less on the token per second with the P99. But it's not bad at all, right? It's a little bit slower, but can still achieve a very high concurrency rate. And as a result, the cost per request is very low because of this, right? And then in terms of the what TGI's verdict is very stable. I think once I push it beyond 60, and then sometimes I start getting a few errors, but it's not like erroring on everything. So if I push VLLM beyond 512, almost all the requests times out, right? So, but this doesn't happen with TGI, and it's very stable, and it has a higher maximum token size, and it has very good concurrency and good throughput. Um, I labeled the cold start as gray because it's not a good comparison. Although it doesn't affect the model inference performance, but it does, affect the startup time. So it's not a side by side comparison. But what I did want to show you is the different options with, the cache in the image using memory, a GCS mount with a VPC, and then download at runtime. So the download at runtime is actually very surprisingly good, as I mentioned. Yeah, so but I guess it's just because the model is relatively small, right? But with others, I can't say the same. So yeah, so basically caching the model in the container image gives you fastest cold start time, but at the cost of flexibility of deploying different models and container size, right? So if you bake it into here, although you get a really fast startup time, but you have to deploy lots of different images, and also when the RAM goes up to a certain size, you can't fit it in anymore, right? So this is one of the issues in there. Um, yeah, but with the GPU right now, you probably can't run models much bigger than the 7B. I tried the 32 billion model for DeepSeek R1. I cannot get that to run in this GPU, so that's too big. It did claim it only needs like a 22 gig of GPU RAM, but it doesn't work. It just hounds forever. I couldn't make it work, right? So that's kind of the three side by side. Okay, it's important to talk about the cost. So this is a screenshot I took from the real thing I've tested. You can see there's different kind of variations, how much it cost in all the options. But the key thing I want to show to you is it's still good to understand how much it's going to cost you in a total, right? So I worked this out based on the 8 CPUs, 32 gig RAM cost per hour, and with one NVIDIA All4 GPU. So basically, the hour total per hour per Cloud Run instance would cost you around 1.58 pounds. It's not cheap, but with the total per request or per user per hour, if you can achieve 60 RPS, which in this case we can, and the per user cost per hour will drop into only 2.6 pence, right? That is an important thing and why I care so much about concurrency and the token generation performance as well per request. Because if you can achieve something like this, it's very, very good. And don't forget, with Cloud Run, you can scale to 0 as well. And that's very, very significant. Okay, now let me show you some of the things I did and also what a real-time graph really looks like in a demo. Okay, so now you can see I've deployed the TGI version of it and the VLLM version of it, right? So apologize for the naming convention, did it in 2 different days. So the the VLLM solution is deployed with you know the R17B model, but the TGI is also deployed with that model. So exactly the same thing, right? Like what I just went through in the slide. So I want to show you the setup very quickly. If I go into there and if I look at the revisions. So you can see here, I've actually set this up with the 8 CPU limit and then 32 gig of memory and then 1 NVIDIA L4 GPU. So there's a few things in there. It's basically just setting up the cache, because the cache directory and the mounting. This is mainly for because this way I've used the GCS fuse mount. So this is how I actually put it in there. So you can see this is the cloud storage bucket where the actual model is downloaded to, right? So all of the details in the code, I'll show you in a minute as well, where all of this stuff is, and you can find it if you want to try it yourself. But the most important things is if you look at the logs, this is already, I've just sent it some traffic, I think just now, to make your life easier to try this. I've also converted the inference code into the Jupyter notebooks, so you can run this in Colab Enterprise very easily. So this you can see I've actually set up a few parameters at the top so that you can replace this with yours on whichever thing you want to try. So right now I'm trying, you see the 60 concurrent request model with the 512 maximum tokens. And this whole thing is basically the code to do some DAG generation code on Airflow, right? So same example as what I used with Ollama. Obviously, I'm not going to repeat Ollama in this demo again. That's, if you want to see those, what I did in that one, you can watch the previous video. So one thing I want to show you is you can see in the logs, right? This is important. You see there's a trigger of the worker scale up. So this, I think, either changed from 0 to 1 instance on Cloud Run, or 1 to 2. You can see at this point, I think it's this point. Yeah, this point is where the container started doing its things to actually Cloud Run started doing its things to get the next instance spin up. Right, you can see the amount of time this took is very significant. So this is 3.5 minutes is coming from here. So this is where it got started, which is 10:12, right? But if you look through all of these other time, it was loading the save tensors, which got like, that's like from here to here is like a minute. And then when it started, the majority of the time was taken in where is doing the initialization of the CUDA graph shades, right? This took another 2 minutes or so, and then it started serving traffic, right? So it started serving traffic after that. So it took, so this, when I was looking at the start, it was around 3.3 minutes, 3.5 minutes. It was very significant, and this happens at every single time when it scales up. So this is obviously can cause a problem if you actually have people waiting on the other side. So you need to be very careful using this solution. If someone has to wait for three plus minutes, having something usable. But once it's up, you can see, like, let me just refresh this page. Yeah, as you can see, it's actually serving traffic pretty nicely, right? So here it's doing. So what I've done in the background is I've triggered this code. So put a 30 request in there, concurrent request, and 512 tokens, because as I mentioned, beyond that, it doesn't work. I can show you in a bit, like what problem it causes. But now you can see this is actually complete. This is all the requests, 30 requests. It took 66 seconds, P99, right? That's very, very efficient. So you see it's returned all of this stuff in the output. If I change it, however, to, let's say, double that, right? This is the issue I've got. Now, it will take some time to run, but I'll just let it run in the background. But the output I've seen previously was this would actually time out on the majority of a request. So while that's loading, I just want to show you some of these things I have already triggered in the, let's say, the last hour on this scaling. So if you look at this VLLM R17B deployment, you can see the container instance count, it scales up and down based on your request. So right now it's at 1. The request latency, you can see that 66 seconds is coming from this here. So you got very good. So the P99, and it goes up a bit, and then is 66 is what actually measures. So this graph is not exactly that accurate. In the code is actually more accurate. And if you look at the container utilization on CPUs, it's actually not using that much. This is why this is why, like, the minimum doesn't require this, but the memory, it does use a lot. So you kind of have to have this memory to deploy this model. because that's not even GPU memory, right? But if you look at below with the maximum concurrent request, you can see this is actually goes beyond 20, kind of started getting to 30. And then the startup latency you see here, P99, is about over 3 minutes, right? This is one of the biggest issues with this approach. GPU utilization is very, very similar to the TGI models. You get maximum utilization. You can adjust this, but I don't know why you would want to do that to have it lower the memory utilization if you can actually go like this. And yeah, so it's this is what's happening. So let's see if it's actually finished. Cool. See, this is finished with the 1024 max tokens. So you see majority of the requests, right? It's just not one or two. It's majority of requests is timed out. So I tried to adjust the number of things in the Docker container, in the setups, in the variables, but I could not see any logs saying what is going on or why it actually caused the 504 timeout. This is the experience I had. But for anything under 512, and this would run mostly reliably, right? That's the outcome I've seen. So now let's look at TGI. So TGI, I think I've also triggered some requests. So this is the TGI one. So I'll go straight into the 60 concurrent requests because this thing is actually a lot more performant. So if I start with this, and then I go with running this one, this is the logs. If I close this one and go back to the TGI deployment. And again, let's see some of the other things I've done in the last, let's say, hour with various kind of stats. So you see here, request latency, it can go up higher when I have more requests that send it to the other side. Here I was trying 60. Container count, it was mostly set at 1. And it sometimes goes to 2 and it goes back to 1. This is actually more efficient from my testing, even better than the VLLM deployment. The container memory utilization is a little bit lower, but not that far off. CPU utilization sometimes goes a bit high, but again, not utilized. So it's always underutilized. The interesting thing here is you can see the maximum concurrent request. This goes to 60 and it's very, very good. You have the container startup latency just over a minute, right? This is important because, as mentioned, this is the one that goes to the internet and then get the models. And then the other two, this one, spot on, GPU utilization up to the top as well. So it's actually the whole container is just about 100% well, like 95% utilized, which is exactly what you want to see, right? If you look at some of these logs, so this is basically, it gives you some good stats as well to tell you. So some interesting logs in here, better than the other two options, is you see the completions, the total time is spent, and the validation time is spent, and the time per token. All of these details you can actually see, so you can work out the stats I showed you there is actually coming from those. And this is currently running. Yeah. So let me see if it's actually finished. Yeah, it finished. So this is all the 60 requests. So this is one that start with 512, right? So you can see the 60 requests with 512 is actually performing really well with only 42 seconds, right? So this with, you can see there's no issues and failures or anything. I can increase this to double of the size, and with 60 concurrency, it would not cause any problems either. So I did not see any issues. It obviously takes longer to return. That's just how it works with LLMs. But the outcome is very performant, right? This is the TGI one, last 30 minutes. Yeah, you can see this goes to 64 again. Container start time just over a minute. And then request latency is very, very good and spot on, right? And container count still stays at 1 at this stage. Okay, now you see this is the 1024 tokens with 60 concurrency, and then the P99 is 85 seconds. This is just amazing, right? Just think about it. This is one GPU, what it can do. I want to show you a few more things on the start. So you can come to this repo. You have the TGI Cloud Run and the VLLM Cloud Run. I put a lot of details in the examples and the readmes. In the example, you have the notebook as well. So I put a notebook copy in there. and in here you have a notebook as well. So you can actually look at exactly what I did in there. You can try yourself. A few things I want to go a little bit deeper in the stats that I put in there. So there's an article I followed, which is this one, from Danilo. So this is really interesting because I basically we had a quick chat on LinkedIn on which discussing which option is better. So he wrote this article. I highly recommend reading it. And it's basically showing you exactly how to use the cloud storage fuse to do the mounting as an alternative solution. So there's a few issues I experienced, but nothing major. I just clarified a few things, and if you do these things, it will work, right? No problem. The main thing I want to focus on is the inference performance. As you can see, I showed you what it was like in the different kind of token sizes and different concurrencies. So you see here this all good. There's nothing wrong with all of this stuff. And when you get to concurrency of, when you get to the maximum tokens of 1024, it just basically crashes most of the time. And even with a concurrency of 5 and maximum tokens, it still crashes and times out. So this is the main issue I had with VLLMs. If you guys know how to solve this, please let me know. But I do not have to solve any of this stuff with TGI, right? Yeah, so the various things I tried. This has got examples in here. With TGI, I had more analysis because it was working better. So you see the main thing here is you can actually I've tested all of these variations. With 1024, you can easily go to 60. This is the one I just showed you with the very high 85 seconds P99, right? That's the ones I've tried. However, I think it's a little bit intermittent when you go with 60 concurrent request with 2048 max tokens, then the P99 significantly increases, and then you got basically about 7 throughput 7 per second. I did start getting some errors. This was once when I tried it, but it kind of disappears afterwards as well. I think this is the maximum you with 2048. You probably don't want to go to 60, maybe 40 to 50. That's where you cap at, and then you can actually, because you can limit this at the Cloud Run level as well. You don't have to let that many requests go into one containers. Okay, so I want to wrap this up with a few future thoughts, right? So why I think this is again important, where the direction of open source model is going. Just to share a few things that from my recent research and understanding. So first of all, if you look at the open source LLMs, they're actually advancing very fast. So since R1 was announced, I think there's a few other ones. This Queen 2.5 Max that I've seen like today, that seems to be beating R1 again. These things are advancing very fast, and the key is once someone open source the model, you can easily, they tell everyone exactly how they did it, right? So that enables all the smart people across the world to advance the models in a very exponential rate, right? So this is what I think is going to happen in the open source world. And that's a very good thing. And the next thing is about distilled models. So the reason I care so much about distilled models is because they are light, right? The lightweight means the cheaper, you can run it in many different places in less powerful GPU hardwares, right? So in this chart, you can actually see there is a one thing for DeepSeek R132B, although I can't make this run in the Cloud Run instance. I was running 7B, right? But you can see it still actually has very good performance in here, in the sense of the 32B, you can see is almost very, very close to R1, right? In majority of the categories. So these are all these you see these are all very, very close. It's not that far off. So from what I've seen, the 32 billion distilled models are the sweet spot of smaller size, but at the same time, like is a very strong reasoning model comparable to R1 and O1, right? So I think that's important to keep in mind, that is not necessarily you need all of these big models. Some of the distilled models can actually perform very closely to potentially what you need with a much less GPU requirement. So Yeah, I think that's important to keep in mind, because as the open source models, especially distilled models, are advancing in very specific categories, and don't forget, you can fine tune these models as well. The smaller size takes less compute power to do those, and then you can keep that to yourself. In with those models would contain the information that belongs to you, belongs to your organization, so they can become very, very powerful, right? The last thing I want to say is, I don't know if you heard about this NVIDIA Project Digits. So it's something being announced, I think, like a 3 or 4 weeks ago. Um, it's basically one of these things that proves that GPU is also advancing fast. So this thing is in combination, it goes exponentially, right? You can see, I would reckon, every single month you see something mind blowing. So this is what I already start seeing, and I think it will keep happening. This is a supercomputer that you can use. Is a box this size, right? That's literally how small it is. But this thing can run. This thing has 128 gigabytes of DDR5X. So the cost of $3,000 includes all of the other stuff as well, right? That's not just the GPU. But this thing, NVIDIA claims it can run 200 billion parameter models just in a box. This is pretty crazy, right? If you think about it. So the one I used on Google Cloud's Cloud Run is the is nowhere near this. That one has only 24 gigabytes of RAM, so it can't even run 32B. But this one, pretty sure it can, right? So what this means is, not only the models are advancing, these new models are getting better. They're getting smaller, and you can actually fit those into a box like this. I can't even start to imagine what it would look like in the GPUs, the options that Cloud Run would be able to use, or the Vertex AI stack would be able to give you different kind of GPU options, and the price would go down as well because of um, the advancement of the GPU itself, right? So yeah, I think this is a very important what is going on in the future. I think is very, very exciting stuff, and this is why I want to spend quite a bit of time comparing the different options. So when you actually have the use case to deploy open source models or have an alternative, it's always good to have this option to spend the least amount of time to get it into production, right? Uh, yeah. So that's everything I've got, and thank you very much. And if you like what I did, if you like what's in the video, add me on LinkedIn. Follow what I'm doing. I try to keep up to date in these things, but not in a hype. I try to make this thing useful, to think about the different use cases I see with the customers I work with, and to share in a generic way, and how this can benefit everyone, right? It's because people make open source models open to benefit everyone. There's no different in what I'm trying to do here. But yeah, thank you very much, and I'll see you next time.